Hi there, my name is Chris Clements. I'm a teacher at Caddo Parish Magnet High School in Shreveport, Louisiana, and I would like for you to join me for my first podcast. I'm going to be telling you about solutions, and you might hear some Beethoven in the background. I'm playing Symphony No. 6, Pastoral, one of my favorite symphonies. You might also hear a black kitty cat jumping up and meowing and jingling, something like that. So please giggle every time you hear him come up. Alrighty, let's go ahead and get started on solutions. Okay, solutions are classified as mixtures, if you recall. There are two types of mixtures, homogeneous and heterogeneous. If it's heterogeneous, it means it is not uniform throughout. But if it is homogeneous, it means that you can take a sample anywhere in the solution and it should be identical. So a solution is classified as a homogeneous mixture. There are two components to a solution, the solute and the solvent. And the solute is classified as what is being dissolved. So if you think of an example of a solid in a liquid, think about sugar in water and think about the fact that the sugar is being dissolved in the water. Therefore, in that particular example, the sugar is the solute. The solvent, on the other hand, is classified as a substance that does the dissolving. Water is generally regarded as the universal solvent, but I don't want you to think that water is always a solvent. For example, if we have a solution of two liquids that are miscible in each other, which means mixable in each other, nice cocktail word there, then a prime example of that would be something like isopropyl alcohol and water. Isopropyl alcohol, otherwise known as rubbing alcohol, you may certainly buy in a grocery store or a drugstore, and it is typically 70% isopropyl alcohol, which means that it is 30% water. And if that is the case, then the solute is the substance that is present in the lesser amount. Well, in that particular case, the solute would be water and the solvent would indeed be the isopropyl alcohol. Alrighty, we're going to talk about some factors that affect solution formation rate. And those factors are temperature, agitation, and particle size. As I talk about each of these, I want you to just think about dissolving sugar in tea, since that seems to be a good practical example that all of the Southerners in the audience can understand. Alrighty, so the first factor is temperature. When I make tea to make sweetened, I always dissolve the sugar when it is still very hot, because the greater the temperature, the faster the sugar can dissolve. Meaning we're talking about how fast it dissolves, not how much can, but the rate at which the solution forms is what we're talking about. So, as temperature increases, the rate of solution formation will also increase. Again, a second factor is agitation. Agitation is a nice fancy word for stirring or shaking. So again, think about when you add sugar to tea, you generally do not just let the sugar sink to the bottom. You would probably put a spoon in it and stir it and be willful to make the sugar dissolve in your ice cold tea, which of course it would do more speedily if you had it, what? Hot. You got it. Alrighty. Third factor, as I mentioned before, is particle size. And while we don't ever really put this to practice, if we were to dissolve powdered sugar rather than granulated sugar into tea, we would certainly get sweetened tea a lot faster. So what that translates into is that the smaller the particle size, the faster the solution formation will occur. Okay, the next topic is Henry's Law. Henry's Law tells us that the solubility of a gas in a liquid is directly proportional to the pressure above that liquid. And a fabulous example of this occurs with carbonated beverages. All a carbonated beverage really is carbon dioxide gas dissolved in water. So if we think about just seltzer water, something like that, or club soda, which are typically just truly CO2 in water. When we think about Henry's Law, let solubility be represented by an uppercase C. And because it's a direct proportion, as you might recall if you've done the gas laws before, Henry's law states that C1 over P1 equals C2 over P2. That indicates it's a direct relationship, which means that as the solubility of a gas increases, the pressure above that liquid in which it's dissolved increases. So again, if you think about a carbonated beverage like seltzer water, when you've not opened it, the pressure sitting above that liquid, above that actual solution is what we're talking about, is very high relative to the atmospheric pressure. When you open the carbonated beverage, you will decrease the pressure sitting above the liquid eventually to whatever the atmospheric pressure is. Well, what that does is allow the CO2 that's dissolved in the water to come out of solution. And it does so voraciously that it drags some of the water with it. Hence, we get to see bubbles that form when that happens. Okay, I'm going to talk about a couple of qualitative descriptions of concentration, and then we'll get into several quantitative descriptions of concentration. Qualitative means without numbers. It's describing the quality of the concentration of a solution. So it's not going to give numbers with it. It's just going to use words to reference how much solute is in a solution. So the two qualitative descriptions we can give about solutions are that they are either concentrated or they are dilute. If they are concentrated, you can simply state that it has lots of solute in it. For example, concentrated orange juice has a lot of orange juice and not much water, which is the solvent in that case. A dilute solution has, conversely, not much solute. Again, if we dilute concentrated orange juice, we do so by adding solvent to it, so we reduce the relative amount of solute. Okie dokie, now we get started on several types of quantitative descriptions of concentration. We're going to start with molarity. And molarity is represented by an uppercase M. If you have difficulty discerning your uppercase M from a lowercase m, I've always suggested that you underline your M to show that it's uppercase. Molarity is defined as the number of moles of solute divided by the number of liters of solution. Your units will be moles per liter, but you may certainly write it as an uppercase M. And you'll often see on a label something like 2 and then an uppercase M describing a solution. Well, that is described as 2 molar, as in the things that we find in the back of our mouths. Alrighty, another quantitative concentration description is mass percent. And mass percent is represented as M/M percent. It is lowercase m's, by the way, and is determined by taking the mass of solute divided by the mass of solution and then multiplying by 100. The mass units are not particular. It's only imperative that they be the same for both the solute and the solution. Because they're the same unit, we end up having unitless mass percents. They have no units to represent them. The next one is mass volume percent, represented as lowercase m / lowercase v percent. We calculate it by taking the number of grams of solute, dividing by the number of milliliters of solution, and then multiplying that by 100. The units are specific, though they can vary from what I've given you. Let's stick with having them be grams per milliliter. Alrighty, the next one is volume percent, represented by lowercase v / lowercase v percent. And rather like mass percent, it is determined by taking the volume of solute, dividing by the volume of solution, and multiplying by 100. The volume units, again, are not specific, but they must be the same for both the solute and the solution, so that we end up with a unitless representation for volume percent. The next one is mole fraction. And mole fraction is represented by the Greek letter chi, which is spelled C-H-I, and represented by kind of a squiggly looking X, kind of an uppercase squiggly looking X. We can find the mole fraction of both the solute and the solvent, so I'm going to go over both methods. If we're finding the mole fraction of the solute, then we will take the number of moles of solute, divide by the number of moles of solution. If we're going to find the mole fraction of the solvent, we will take the number of moles of solvent and divide by the number of moles of solution. Again, since we're dividing moles by moles, we end up with a unitless value here. It is numerical, but it is unitless. And something I would expect you to notice is that if I were to add the mole fraction of the solute to the mole fraction of the solvent, because they are decimals and they've not become percentages, their sum will be 1. It's a handy way to kind of check yourself when working mole fraction problems. Because of rounding, sometimes the sum can be a little less than 1 or a little more than 1. We just have to pay attention to what our rounding does to that effect. All right, and a final quantitative description of concentration that I'd like to go over with you today is molality. It sounds like I have a speech impediment when I say it, so I will spell it for you. M-O-L-A-L-I-T-Y. It is represented by a lowercase m, so as not to get it confused with molarity. It will never be confused, by the way, with meters, because we'll never be measuring length when we're talking about solutions. Molality is determined by taking the number of moles of solute and dividing by the number of kilograms of solvent. Its units will therefore be moles per kilogram, but just as with molarity, we can use its lowercase m to represent its unit as well, and it's understood. So if you were to see on a label 2 lowercase m, it would be described as 2 molal, which is M-O-L-A-L. Again, it sounds like I have a speech impediment. Okay, something else I'd like to go over with you is a really important concept that I use so often as a chemistry teacher and that so many folks use in labs. It is definitely worth learning. It's a concept of making dilutions. I stress this because we don't want to have to stock every concentration of every, say, acid that I would ever want to present to my students. So what I do is stock the most concentrated form of any acid I plan on using. And from that concentrated form, I can make whatever dilution I need to make a particular concentration. Well, the formula that I use over and over to determine how I make that dilution is as follows. Uppercase M for molarity, subscript 1, times uppercase V for volume, subscript 1, equals M2 times V2. So that we're really looking at an initial molarity and volume and at a final molarity and volume. The rule of thumb when you're making a dilution in a beaker is to add the acid to the water. You've probably heard this at some point and learned it because if something is going to splash, it would therefore be the water that would splash on you rather than the acid. However, I don't tend to make dilutions in beakers. I tend to make them in what are known as volumetric flasks. Volumetric flasks are really cool blown glass devices that are calibrated to give me a particular volume when the bottom of my meniscus is on an etched line on the neck of the flask. It's a really unique looking flask that kind of looks like, I'd say, an onion with a big set of roots on it. It's a bulbous bottom and then a really tall skinny neck. And on that neck somewhere again is an etched line. So what I do when I make a dilution, for example, today I made a 6 molar solution of hydrochloric acid. However, I did not start with 6 molar hydrochloric acid. I started with 12 molar hydrochloric acid. And because I wanted 6 molar and I wanted 500 milliliters of that 6 molar hydrochloric acid, I poured 250 milliliters of 12 molar concentrated hydrochloric acid into my 500 milliliter volumetric flask. I then added water until my fluid meniscus reached the etched line. So I then had a 6 molar solution of hydrochloric acid. Okay, well, I hope that helps you tremendously. And if you need some practice problems, I have uploaded my PowerPoint to my website, which is on Google Pages. And if you'll just, I guess, do a search, since I can't remember the website address right now, for Chris Clements on Google Pages, you might find it. If not, I'll give it to you later. Thank you very much for joining me.